to start today's talk. Before that, I know many of you are new to this. This is the second time we do this AI for intelligence analysis lecture series. So I want the director of the center, ICCAE, Ava Majalasi, to give say a few words about the program and the lecture series. Ava, please.
Thank you, Dr. Chu. My name is Ava Majlesi. I oversee the Rutgers Intelligence Community Center for Academic Excellence, otherwise known as the ICCAE program. And we are a consortium that includes faculty and students from Rutgers University, City College of New York, Borough of Manhattan Community College, and New Jersey City University. Welcome and thank you for joining us for our series on artificial intelligence for intelligence analysis hosted by CCNY. The purpose of this series is to make connections between technologies and applications and to enhance awareness of the importance of artificial intelligence in national security contexts. The speakers in this series are active researchers and practitioners in using AI, data analytics, and machine learning techniques in defense, intelligence, and security applications. Before we get started, once again, I want to thank the Office of the Director of National Intelligence for supporting our students through the ICCAE program. Through this program, the federal government provides grants to public universities to enhance the recruitment and retention of a diverse intelligence community workforce that is armed with the capabilities that are critical to the national security interests of the United States. So, why are we talking about AI in a national security context? Well, we know that artificial intelligence impacts national security within the United States in three key areas: the success of our military operations, the robustness and accuracy of our intelligence gathering, and also economic superiority. So the IC has an interest in a future workforce that has advanced technological skills. So for the students that are here today, I really want to encourage you to become more involved with our ICCAE program. I think what you're going to find is that you already have so many of the skills that are necessary for a career in the IC, but I think our team can help open your eyes to professional development opportunities that are going to help propel you into that field and into intelligence-related careers. We have a website where you can learn all about our program, all about the events that we do to help you gain those skills that you might need. It's intel.rutgers.edu. I'll put that into the chat for you. Again, I want to thank you for joining us. I hope you find today's session informative. And I'm going to turn it back over to Dr. Chu from CCNY, and he is going to introduce today's esteemed speaker. Thank you.
Thank you, Ava. That's why I wanted you to do the introduction. So you know what? I'm going to do a very quick introduction to Erik, and so that I can allow him to do the career story he say about himself, because he start to talk about his work. So Erik is a program officer at the United States Air Force Research Lab, AFRL, and also Air Force Office of Scientific Research, FSR. Previously, he was a principal scientist at the Air Force Research Lab in Rome. And before that, he also is an exchange scientist for the Canada Defense Research Development in Quebec. And also an information fusion evaluation tech lead at the Air Force Research Lab in Dayton. That was the time I met him in his office. So he came in, I still remember that day, right? We talked with each other, and after that, we worked on a number of projects. It's a really enjoyable experience working with the researchers and the program directors over there for very cutting-edge researches and higher priority national needs. So Erik also served numerous academic roles as an adjunct professor in electrical and biomedical engineering at 12 universities, as well as he is also a colonel retired in U.S. Air Force Reserves. So without any further use of the time, here's a long list of the publications, include the number of books, as well as the fellow of IEEE and the fellow of SPIE, very notable institutions in our field. So with this, I'm going to give the floor to Erik to start the talk. By the way, the talk, he's going to do career talk and the technical talk. And then after that, we have a QA session. So if you didn't pay attention to my email, so you send your question in chat. I'm going to collect them, compile them, put it in a Google document. So moderator today is our star student, Steven Alzheimer. I hope I said his name right. So to present the question to Erik. Erik? So you can share your screen. Stop the sharing.
Okay. All right, here we go. All right, are you able to see the screen?
Yeah, perfect.
Okay, great. So I appreciate the opportunity here to present some ideas. The main elements of this presentation are actually posted on the ARVIX site. So we have listed a multi-source AI scorecard table, and we're trying to utilize that for system evaluation of different techniques. So many of the topics that are discussed here, you can receive, say, from the publications that are listed on the slide deck. Now, it was given to me as to provide a career overview, and much of my career is listed on various biographies, kind of like the one that was attached here. However, I'd like to start further back. So when I was 10, my dad had this book, Foundations of Orientation and Mobility. And in that book, the goal is to find ways to augment the ability for low vision or blind people to get around in the environment. So I grew up with a lot of psychologists, engineers who were actually trying to find ways to use technology to assist handicapped people in their ability to get around. That includes 4 of my family, all PhDs doing this research. And I wanted to say, okay, technology could really help. So in that case, at an early age, I won a state science fair, and then we won robotics contests. And that basically solidified my interest in the topic. So if you're thinking, okay, sensory substitution, if you don't have vision or you have low vision, what else could you substitute it for? Well, you could use audio information, you could use camera feedback to then tactilely help the solution. And in this case of doing the basic research for those tasks, at least in the case of my father, right, the long cane, which is not automated, is still one of the best ways for humans to get around. So instead of just building and creating lots of technology that is costly, expensive, something that people can't afford, it's better to think about how do you construct the environment. So at that time, there was the ADA, American Disabilities Act, and they're now created a lot of things that you see in the environment, such as the sonic things at the traffic lights. So it's a way of thinking about, okay, what is the holistic, contextual information, which kind of proceeds through the topic that I'm going to talk today. As far as the methods, we all need some support. So I took a scholarship for undergraduate and then followed into graduate school. And from that appreciation of being able to study, explore something of interest, supports people, students, and then at the same time, if it's something that you really enjoy and you're passionate about, you're able to do that for your career. So I was assigned to the Air Force Research Lab. At first, it was called the Avionics Lab. But then when I had to make a career choice, I stayed on with the Air Force Research Lab as a professor, a military reservist, and a researcher. And I've had the opportunity and the pleasure to continue to explore data, information, multi-intelligence fusion, and get to interact with a lot of people. So with that, hopefully each person figures out what they're interested in, finds the path from which they're able to follow through on that and maintain continuity of something they are getting paid to do that they enjoy, but also internally they want to solve problems that they think are interesting and beneficial to the community. That's kind of a quick story there about the history. As far as the abstract here, I tried to highlight 4 things that I wanted to get across at a high level. One is any intelligence system has to think about it holistically as a system engineering problem. If you develop certain tools and techniques for the analytics, that's not completely the answer because someone has to make decisions on that. The tools and techniques have to answer questions people are looking for. And with that, if we have the push for what the intelligence community was going after, they were talking about autonomy at rest, which is take all the static data that you have, do some analytics on it. Or you could have the opposite, which is autonomy in motion, which is kind of like a driving car, which now has moving video, and try to analyze that in real time. The problem is, if you don't have consideration of who's the user, whether it's the actual car or the driver, you're going to have a problem where dynamic data that's being processed is not augmented with the data at rest. The key elements here then, as related to the foundations of what research I was trying to include, if you look at data at rest, that'll be your contextual information. So if you had the terrain networks of the urban areas that the cars drive on, where the pedestrians typically cross, you then can use that information to cue, say, full motion video analytics to determine if people are crossing the street, if the lighting conditions are bad, whether you can rely on the elements to actually analyze what's happening, discern if people are crossing the street, and be able to use that effectively for safety and security. Next, as indicated there, you have a combination of sensory data, which is usually based on physics, and you have human information that needs to be combined. So one example here following the thread is full motion video. We obviously have target designations, semantic information, and the semantic information, typically in the form of a dictionary, is usually human-derived. If we're going to talk about a person, right, the person doesn't actually mean anything to a sensor. It's actually something that's human-derived, a human concept, and we need to fuse both what the human's interested in and what the sensory data is giving us. And then lastly, we've introduced Multisource AI Scorecard Table. It's based off of the Intelligence Community Directive 203. So it has a nice consistency with this center on how to actually support analytics and use of AI. Now, it looks like this got reformatted, but in a series of books that we've published, many of the topics presented here are available, which then focuses on the physics-based and human-derived information fusion. So in the talk, I have a couple ideas I wanted to motivate. We start off with the human decision-making, the data fusion. We then move into the second part, which is currently what's needed for the community, or at least the discussion on trust, and then trust in AI. And then finally, some of the challenges going forward, say on scalability for the analytics. With that, there's the scorecard table that's available, as well as some documentation in the motivation and the directions of these techniques. Okay, so if we start off with something easy, intelligence community, if you haven't heard of the Observe, Orient, Decide, Act loop, it was created by Boyd. It was revisited over and over. It's a nice way to discuss what's going on. With that, there's the element of, say, the human that you need to think about, such as cognitive engineering, about going from the ability to make decisions to selecting sensors to observe. Once the observation area of interest is decided, such as an urban area, there needs to be some sense making. The sense making then utilizes the data analytics to orient what's going on. There's some level of dashboard analytics, which might be alerts or warnings, such as if you have recognition of security challenges, people entering the wrong buildings, then it's going to be able to highlight that, warn someone, cue someone, and then that affords that group or people to make a decision, and then they can collaborate with the system. So in this case, we have mission effectiveness on the left, right? The actions have to be effective, such as humanitarian relief, disaster response. And on the right, we need to prepare these tools and techniques and people such that it's based on the scenarios of interest, such as responding to a fire or a hurricane. Two of the challenges that exist currently is scalability. how much do we want these tools to interact with the big data? Is it going to incorporate all of the IoT information? Is it going to respond in a way that allows users to appreciate what's going on? Clearly, the human can't process all the data, so a machine can help with the reduction of the data to the key salient points to be able to do that. And then if we do have interest from these tools and techniques with the humans, then they've got to trust it. So two of the key issues that need to be considered now are scalability and trust in the delivery of these systems. If you see within the DoD principles, they have various techniques, and I'll highlight later, but on the right, you can see one of them is trusted, linked, and understandable going forward. So in the elements to do the scalability, we need to think about large data sets. So in the first round, we think of the sensor as a typical processing loop, like a Kalman filter. It's going to do the physical measurement, do the update, reduce the uncertainty, and provide feedback and control for itself. On the other hand, if you don't have access to information or data that you've seen for all the scenarios of interest, such as responding to a unique event like bombing or the Boston Marathon, you'll have to go ahead and use some augmented approach, such as simulations or other methods to create data based on physical principles or the training information to determine if the analytics will respond correctly. So with the push from AI and machine learning, one of the challenges is that most of the time these groups are processing data that they've already seen. So that would be like autonomy of motion, say for full motion video. But we need to create instances where it's affording the development of these AI machine learning systems to be more robust to situations that they haven't seen, which requires to augment the data. One popular technique put out then is the generative adversarial networks that allows you to take some representative physical data, manipulate it to do the discriminator, generating the discriminator to determine what's going forward. With that, the idea here is, at least one of the things promoted in this presentation, is autonomy and use. Not all the data is going to be necessary, not all situations are going to be necessary. So we do have to think about what's important, what's usable, and what would be key to do that. The usability of, say, data within the models, usability of the models, all of those are going to be things that help in scaling for effectiveness and efficiency, say over time and space. And one example here is the ensemble Kalman filter, where you start with lots of models, and then you do a model reduction to the ones that become most representative for the situation that it's deployed. We have in the book quite a few examples for this, for measurement aware, for uncertainty quantification, contextual awareness, such as target tracking, and then cyber awareness to be able to determine what's happening in different techniques. And as demonstrated for the community, right, the energy aware power computing, after the recent attacks in the last month, these professors were in high demand based on being prepared, say, for contextual models of power plants, and then taking the IoT data that was being used and being able to fuse that data for decision making, especially in situations that we're not prepared for prior to the events last month. So with this, as we look at the systems analysis, one of the things that we have to assume is that people typically looked at trusted data. So if you have a control system here and you have the blue boxes, they assume that the data that you're getting is trusted. You'll run it through a system model. You have the sensor feedback, the sensor data is trusted, and then the output is trusted. So if you have full motion video and you're watching the system, you have a nice tactical approach to understanding what's happening. Someone can see the analytics in the video, and sometimes they can trust it based on the believability of what they see. If, on the other hand, the machine analytics is overloading the video, the complexity, then the user will scale back the analytics to be able to trust what they see. If, on the other hand, we have data and information fusion, and we want to combine lots of different data sources, it's difficult to present a combined approach to the user. So here we have now scalable issues where we bring in lots of other data. We now want to run it on machine learning and intelligence that has black box systems that are hard to interpret. What are the features? At the same time, the fusion methods they need to be scalable across these approaches, and now it becomes slightly intractable, for the human to understand all of the data analytics that's happening. Then you need to reduce that scale back to something that the human trusts, and that's kind of the open problem that I'm advocating for in this presentation, and that brings us back to autonomy and use. So what data would the user trust? How is it going to be derived from the scalable system, and really that interface between the man and machine to effectively produce, a product? Now, in the ability to do this at scale, right, the trusted approach is the needs. We want it to be secure, robust, durable. We want it to be scalable. So there's lots of different techniques out there on data fusion, machine learning, deep learning, cognitive radios, software-defined radios, software-defined networks. A lot of these kind of coordinate into a combined effort, which is certifiable AI ML. Certifiable AI ML does it actually meet the performance bounds? So if you're able to create a measure of trust, then you can certify something if it meets the trust performance bounds. And this is currently a contemporary issue of concern, but if we know what the performance requirements are, we can design, test, and certify something all at the same time if it's going to meet the needs. And that's critical for the IC community, because a lot of times we'll develop some technology and it takes quite a while to get that technology into the hands of the users so that they can operate on certain scenarios and situations that they're responsible for. So we have multi-resolution trust. We have the human-derived and the physics-based information. Is a human going to trust another human based on what they've written? Are we going to trust different types of sensor modalities? I guess explained with the full motion video, you might be able to see and discern what it's looking at. But if the video has lots of blur, are you going to look at that? We usually use some techniques in multimodal computing that supports filtering, get out the good data. We then bring it into our sensor fusion model. Now the question for output is, are we going to trust it? So in estimation theory, you can usually reduce the error, such as the spatial error probability that you're looking for. Can we use learning over different techniques to basically enhance the performance of these systems, reducing the error, increasing the ability? So with that, it's a systems engineering problem, because you have the human to think about the cognition, you have the hardware that's going to be able to execute these techniques. We have the software. That software, while it might perform well in certain situations, it has to be assured that it will do its performance. And then, of course, a lot of these things, underwriting the success of a lot of these is the actual data. So if the data is good, you have a good chance that the tools and techniques can support that by reducing the uncertainty. On the other hand, if the data is not, sourced well, or it's not, effective, it's not going to be resulting in meaningful outputs. So with that, the military has, and ICE has processing, exploitation, dissemination. So we would like, on the left side for the processing, we would like to automate more of the sensor. On the right side, we'd also like to have products that immediately can be disseminated, and in the middle, allow the analyst to spend more time doing their exploitation, using their sense-making ability to understand a situation, determine what's important, and then immediately say output the report, which has both the key elements of what happened, the scenario response. And when I briefed these many times before, it's more like a the 2-minute summary of a sports game. You don't need to play all the game back. You just present the highlights. So if we can do the analytics process when the key events happen in the sports, then the analyst can go in there and look at it and output some commentary, and then immediately the video is packaged, say in a 2-minute summary of the entire game. And that's the kind of scenario reporting that is of interest to inform commanders and decision makers on how to react. And there's the analyst. So within this focus on being able to summarize events, we have a couple different situations that were highlighted recently. So one, we are working on ontologies to support urban air mobility. So if you have multiple UAVs flying around the airspace where say the drone 2 and drone 3 on the right are cooperating with the airport. They have the appropriate communications and semantic definitions provided, but then you have an adversarial drone or one that's non-cooperative that you're unsure about. How are you actually going to, deal with that scenario? At the same time, in the middle there's wildfire monitoring that we're interested in. Then there's weather hurricane analysis on the lower right from Erik Blasch. And then in Maryland with Dave Pauly, there's the ability to coordinate multiple UAVs to respond to situations. And so with that, you can see that there's a lot of need in looking at the push for urban air mobility, air transport, air delivery, and figuring out how we're going to support that. At the same time, we have applications in space analytics, intelligence, surveillance, and reconnaissance, and have data sets available for people to try out multi-resolution data and information fusion. Okay. Now, information fusion, as I highlighted here, one of the key things from the book and the teaching materials is the evolution of how the processing model for information fusion came about. If you look on the graphical picture, we have level 1, which is called object assessment, which is your typical tracking and identification. That constitutes a majority of what people are doing. That's explicit fusion from the machine. That assumes that the data from level 0 has been pre-processed, organized, and made available to the sensor. The challenges for the community are really in the green box, which is level 2, level 3, situation and impact assessment. The challenge is, what is the situation? How do you describe it? How are you going to make that available? So if you're tracking all the targets in the city from overhead imagery, does all of the targets need to be presented? And that's where the human decision-making is critical. Typically, say if you have overhead imagery, you're looking at where the congestion is happening in the city, where there might be an accident, how are you going to reroute people? And all of those depend upon both the sensors that you can process, say level 4 process refinement, and then what is the mission? Are you trying to maintain safety, analysis, and situation awareness? So from that, the elements associated with machine learning, common filtering, a lot of those focus on level 1 object assessment, whereas the higher level information fusion challenges really exist in defining a situation and where to go from there. So just to to give that pipeline, you start with the target sensors. You're doing the level 1 tracking and detection. You're outputting some decisions, but how is that going to be important to the human? With that, there are a lot of things that could be leveraged. One might be target models of interest. Say, what do the cars look like? Then, can the data be registered? Can you use sensor management? Do you actually have the accurate sensor models? Do you know the camera parameters? Do you know the affine translations that go with that? Do we have models of the environment? There's not only just the spatial dimensions that you might get from Google Maps, but can we actually get the lighting conditions, and can we actually incorporate that into the analytics and the decision making? That then builds into a performance model. So if we're able to do performance model, that can lead support to the sensor management of which sensor to use and which one to actually take analytics on. And then we can adapt based on what the humans' choices are, and be able to then characterize it to the behavior and the mission that they're looking for. So all of these are elements that support, say, just the object assessment. If we had a similar approach for situation assessment, that would really aid people. And for 20 years since I've been doing this research, there's still not great opportunities to determine what is a situation. Okay, so this is the same chart repeated here for discussion. So the meaning and the performance and the information are critical. Situation awareness is a function of the meaning that you're interested in. A second challenge that I wanted to highlight that's typically unappreciated is the actual information management. So a lot of times the information that you actually want to process goes through lots of other types of pre-processing before it's actually presented to the presented for fusion. So it has to go through a security layer, workflow, quality of service, there's brokerages, and someone has to maintain it. and then you can get access to the data space. So if you're able to do this, you have to do this, concentric access for all different types of services, and that sometimes precludes the ability to deploy sensor and information fusion systems to users who are looking for that. So with this, in the book and in the teaching material, we have different layers that are of interest. So for example, if I want to take the transformation layer, people have to normalize the data, contextualize it, be able to determine what's usable. Once that's satisfied, then a broker will determine if the information can be disseminated to the right people at the right time. If we redraw this, it's the same kind of approach, but now incorporating the information levels, the object assessment, we're going to have that on the outside. But even if your video camera is doing its analytics, it still has to go through a security layer to determine if the results from that, say, privacy and other concerns, will actually be delivered for people for analytics, such as security or police officers. The sense making, there are quite a different models out there about sense making. It's underappreciated, but typically you have to kind of work with the users and the humans to understand what is their cognitive workflow, what do they need to make sense of, how are they actually going to use the data and the information. And then on the layered sensing, also what kind of say graphical user interface, which we call user-defined operating picture, or UDOP. How are they going to work with the UDOP and pull out the information they need? So for example, following the thread of full motion video, right? You can stare at the video all the time, but it won't give you a situational analytics. It'll just give you kind of a focused area of knowledge. So you're going to have to figure out how different people use the tools and techniques within their own needs, and then continue to tailor the products to support that. So we have the scenarios and the information, the user, awareness and estimation, we need to bring those together. Scalability is, can we develop the theory to have performance prediction models? And on the right side, awareness really comes into trust. If the tools and techniques support the situation awareness, the user will gain more trust in the analysis. So it's really what is called human machine teaming. The machine can do the scalability, and the human can work with the machine to trust the output. So back to the slide with the OODA loop, we want to be able to utilize such things as agents. In the agent-based approach, we have information fusion agents, control diffusion agents, and then we have infusion agents of humans, infusing the humans with the actual techniques. That leads us to the UDOP that I highlighted, user-defined operating picture, to support the techniques. Building on the thought process that comes with that is the fact that if we have multiple OODA loops, you might consider an OODA loop that comes from a human, where they're trying to make decisions, but you also might have an OODA loop from which the machine is trying to make decisions. So one of the challenges that we've tried to highlight over many years is that the data to decisions paradigm isn't exactly correct. So if you look at the bottom, data to decisions assumes that the machine is going through all the data and then outputs decisions to the user. If the machine analytics were designed by an engineer, and then the human who's doing their job, like a police officer, has no knowledge of the engineering approach, the question is, does the actual decisions that are being output by the machine actually help the user do their job? If not, the machine will be turned off and no one will support it. So we need to have a combination of decisions to data and data to decisions. So the human is saying, well, I need to observe a certain area. That's the red box. It's an area of interest. I need to find out, information that's relevant to what I need to be responsible for. So I'm asking the machine for decisions that I'm interested in. We're going to, query the machine to go get the data, to do the data analytics, do some decision approaches within the machine analytics side of things, say outputting the highest probability or the plausibility of events, then putting that into a package, say observing, what decisions are important, and then sending that data back to the human decision or human for such prioritization of relevant information to their needs. And so having a combination of data to decisions, decisions to data really helps streamline the human machine teaming whereas typically people overlook the importance of the human who are utilizing the machine and just design things they think are interesting and relevant. So now, to be able to enable that, there's a data as a service approach that's of interest. And in this case, some of the techniques that we highlighted was data and use. Now, the report actually came out in, I think, November 2020, but we had basically organized this. And at the time, the goal was vault. The data should be visible, accessible, understandable, linked, and trusted. So to build trusted systems, as highlighted, you need to have a service for the scalability and the data and use for the trust. Since that time that we put out that information in 2018, which was then officially signed off in November 2020, there were other groups who put out principles, say, for the AI machine learning. And if you look at the consistency that comes out each time, and then there's another one from NIST, you can see that if you have the center part, you know, there's the compliance issues, which are the lower boxes. You have the governance issues, which are the upper boxes. In the middle, you have what the user is interested in, right? They want responsible AI. They want techniques that can be understandable, and then they need to be accountable, meaning that if the decisions are being output by the analytics, then the human is going to take action on that. You know, better be able to understand and determine if that's going to be represented. Now, if you take, say, 2020 as the most recent, you know, there's a need for transparent, interpretable, explainable techniques, which many people are working on, and progress has come forth. And then inherently in all of these, how are we going to measure these things so there's a performance bounce, they can be certified on certain techniques. Okay, and then, you know, other things to think about is there's trust versus trustworthy. So if you're not familiar with the discussion, right, things can be trusted or they're trustworthy. And the ethics, legal, social implications of these things, you know, are important. And even with my colleagues in the Air Force and the Air Force R, you can see that they all foundation here, at least on the bottom, you know, they have a shared situation awareness, but metrics. If we're going to create some tools and techniques, we're going to have to be able to measure these things. So the more that people are trying to come up with metrics, say mathematical approaches to measure these things, the better it will be for the community, so that we're all measuring the same thing, just like error uncertainty that we get, or error that gets with a machine learning technique. So if you look at factors of trustworthiness, that's the human factors community. They talk about ability, integrity, and benevolence. If something is benevolent, can you actually trust what's happening? They also have understanding that there's a perceived risk. So the risk in trusting someone else is something that you have to account for. On the other hand, and that was developed in the 1990s. And at the same time, for trusting, are we going to trust in a machine capability? They have performance, we have credibility, timeliness, and there's uncertainty. So now the goal here, say from the machine analytics of trusting and the human side of trustworthiness, there's an opportunity, such things as Bayes risk analysis, that can actually align the human needs of trust and the machine levels of trust. And that was discussed, say, in the textbook here on the situational awareness model from Ensley, because in that case, the perception to comprehension is trust. We don't necessarily have an equivalent on the machine analytics side, which is the assessment side. So there's a need to incorporate that, say, align the machine and the human going forward. Likewise, we've had techniques that build on that, the trust dimensions here from '96 that we just highlighted. But there's people can overtrust. You look at the graph on the right, they can overtrust systems or they can undertrust systems. So we want to build systems that have the correct ability to trust, that align, say, the user knowledge with that of the system reliability. So if the user is getting the information that they need and they can interpret it, and the machine is producing what they have seen, there's going to be high reliability is going to be the correct trust. So we don't want machines to do everything, because if the human overtrusts something, they'll make bad decisions. This was also highlighted, Jinghee Hee Cho. She now at Virginia Tech, has quite a bit published on this. And as you can see here, the point is that even with her publications in 2011, there's scalability, security, and trust, which are being revisited again. And we have, trust stacks that are be able to do that. And on the same, approach, you have the hardware to trust, the user, the application, the machine, and the network. So there's quite a bit of techniques. And in my case, the goal was to look at Bayesian cases that are too delayed. So you're going to utilize evidential reasoning towards that. And with that, I highlight here the Army Research Lab evidential neural network, which basically in 2019 demonstrates the ability to have timely responses, accurate ability to measure the uncertainty, and risk analysis through a evidential deep learning neural network. Okay, so the scalability, we have graphical networks, ontology, we have to trust it, we have to have measures of veracity, and then we need to have trust mechanisms. Okay, so machine learning, I assume the group knows that. What I'm going to highlight here is the ICD 203. So for the ICD 203, Intelligence Community Directive 203, there are these analytic standards on the right. It has 9 levels: so sourcing, uncertainty analysis, distinguishing, analysis of alternatives, customer relevance, logical argumentation, consistency, accuracy, and visualization. These were defined by the intelligence community. It is a good way to align your techniques with what is needed. We can have it in a systems engineering approach. And what we tried to do was develop this to something that was consistent where they're going to have like a product label, in this case, like a soup label on the end, tells you what the machine learning is supposed to do and what it can't do. So in this case, a multi-source AI score table, or the MAST score table. So if we look at data fusion, the whole goal of data fusion is to uncertainty analysis and uncertainty reduction. So clearly, if you're able to bring in multiple data or multiple sources, you're actually helping in the ICD on the first 2 levels that you're interested in. As you can see from the right pyramid, much of the ideas I talked about before are actually the unacknowledged challenges, such as how are we going to collect data, how are we going to move the data around, and then transforming it. When it gets transformed, then for the dark boxes, you can actually do your data learning and machine learning techniques. So there are a lot of things that need to be thought about from the IC community about how do you actually prepare the data, and that then leads to successes, say in the machine learning or the data learning, and then incorporation, support to the human. So with the human, then the ICD that you should look at focuses on, say, distinguishes judgments, analysis of alternatives, and customer relevant. With those 3, it's really trying to say, how does the machine analytics support the user in their decision-making and their situation analysis reporting? Does the machine output only one choice, such as a Bayes approach, or does it output multiple approaches with the correct level of uncertainty, such as the evidential reasoning approaches? With that, there's a lot of interaction the human's going to have with the machine, say in levels 3 through 6. And then the output, if it's going to have consistent responses to the user, they can narrow it down to things they're interested in, such as query-based approaches. It doesn't have accuracy, and does the GUI or the visualization work well with the human? So with this and Rutgers, we have examples shown where we're trying to utilize a scorecard, pick a rating scale, say 0 to 3. And one of the ideas here was that this tool was designed by analysts, for analysts, with analysts. So over a decade, we've been building the product, say with people from Rutgers. And with that, it's tailored to the user's needs. So it's customer relevant. We provide the top assessments they need. And so using the scorecard table, it definitely forces people to think about, what does the analyst want, and then be able to score it correctly. On the other hand, if we want to improve the MAST scorecard, let's say level or the standard 8 accuracy, we can then bring in trust, trust in measurements in standard 8 to determine if it's working for the analyst. So with that, the trust challenge is explainability and trusting. If the data is not sourced well, the pyramid gets out of support. So if we look and turn the pyramid over and we have the deep learning as the output, is that going to be a function of how the data is collected, tip the balance one way or the other, such that, being able to have pedigree on the data collection affords someone a better chance to explain what's actually happening. And then we want to have, explainability. That'll bring it into our UDOP, and then it makes it much easier to certify something that the human analyst will actually want to do in their cognitive decision making. And most recent then, we have accountability, explainability, interpretability, and we need to have these performance bounds and transparency. Okay, scalability is the last one. Basically, the graphical networks affords a chance to do that. Fusion at scale works well. We've demonstrated this for different examples. Tao was in on this one to be able to take and combine the full motion video with the analyst chat with the contextual information and be able to increase the usability of these techniques. And that was exciting because, like I said, Zhang student Tao worked on this, Wang, and then finalized with the graphical methods to be able to align the graphs to have a scalable fusion system. Inherently with that, the streaming video and chat, we had the information management that I described earlier that made it scalable such that you can combine and fuse the information of relevance to that environment. Most recently, we've worked on these SIBRs techniques to do domain adaptation. So can you adapt the data in one domain and support it going into another domain and incorporating transfer learning to help prepare these systems. And then finally, the submodular functions is a way to theoretically have the performance bounds by being able to present data that has a large improvement versus removing data that doesn't scale or have an economy of scale in the results. So with that, the trusted area for scalability, we need to have resilience and data analytics. Some of the techniques that we're looking at is graphical neural networks, generative query networks, game theory and reinforcement learning for these techniques, and then responsive to adversarial attacks. And one of the key elements here is the Army Research Lab on the top has a group called Distributed and Collaborative Intelligence Systems and Technology Program, and they're producing quite a bit of papers that are relevant to the group. So in summary, I want you to take away a couple things. One is the OODA loop is a common reference framework that most of the IC community understands. Two issues we're trying to deal with now is data scalability, such as big data, and trust for man-machine systems. And then we have posted our multi-source AI scorecard table that can incorporate some metrics. And then finally, information fusion for situation awareness is based on the physics and the human-derived information. It's not all about sensing, and it's not all about, say, text analytics from the human. It's actually the combined element to bring those together. We need to come up with metrics of trust, which is highlighted here in the yellow box, and the methods going forward. So with that, I appreciate your time, and we'll be able to take any questions.
Thank you, Erik. So we already have some questions here. I think Stephen may share the screen with the questions, so Erik can also see it. So other people, if you guys have questions, if you can, just put it in the chat. Otherwise, just wait a little bit, okay? So to see we can, after the post the question, you can just talk, okay? Could you zoom it up really?
Yeah, a little more. Okay. Yeah. So first question is, what types of preparation should be taken for a student to get a chance into intelligence analysis?
So one of the things that, at least my own perspective opinion, is that the ability to get into some of these groups and agencies is a function of either summer employment, where you get a chance to work for a group, decide if it's of interest to you. They're going to want some skill sets that you bring to the table. So there might be the first offer, which is to let students do summer internships. So with the Air Force Research Lab, we offer lots of summer internships, and there's no real requirements for people to show up, but you get a lot of experience to understand what the government problems are. On the other hand, there are certain cases where they would want someone with domain expertise, and clearly as if you read the literature and you see what are the current hot topics today, such as machine learning, then companies and groups will want someone who has that knowledge. If you're able to take a class, be up on those techniques, that'll be great. When I was growing up, it was all about aerospace engineering. And at that time, in the early 90s, the aerospace industry went down. So most people who were doing aerospace engineering had to go and change jobs. So for example, I did control theory and just moved into other industries. In this case, machine learning will probably stay for the data analytics, but maybe 10 years from now, it might be another domain specialty that people are interested in.
Zigang, I have a question.
Please, yeah. So just one.
Oh yeah, Erik, this is Kaliyappa Ravindran, Ravi. Actually, we have met like many times in Air Force Research Lab. I've been one of the regular visitors to Air Force Research Lab in Rome, and we have had many hall-time discussions as well as in your office. Anyway, I have a few other colleagues too in this participant list who have had many stints at Air Force Lab, like Professor Soundararajan, Ram Narayan, Larry, many people. Anyway, my question specifically about the use of AI tools for a problem that arises today. See, disinformation and fake information is a security threat. I mean, it's not just spreading false information or not. It can cause social chaos in the system. It becomes a national security issue. How do you apply AI machine learning techniques to detect fake information? I have done some work with Kevin Kwiat, and Dr. Paul Ratazzi at the Air Force Research Lab. We use replication and voting mechanisms to reduce the detect false information, if we can. But I believe that there is more systematic use of AI techniques needed to detect false information. Like whether you read Washington Post or New York Times or LA Times, you look at all of them from heterogeneous sources and then combine them to come up with a good analysis of fake information. Do you have some thoughts on how you apply AI techniques or ML techniques to detect fake information?
Okay, so I have three comments to make it easy, right? So obviously, deep fakes and other things are of interest to the groups. So my personal opinion is, let's start from the adversarial machine learning, right? There's a couple different ways of doing the adversarial attacks. You can attack the AI machine learning model, you can attack the data, and then you can attack the network. So with those three things, right, the attack, say, on the data is this, spamming bad data. So just retweeting things doesn't make it more, accurate, right? You can put out as much fake information as you want, but if you keep fusing all that bad data together, you might, infer that that's, having an impact on increasing the confidence. But in reality, it's all the same source, it's the same data. So you don't want to do data fusion by just fusing the same data over and over and over because there's nothing new. So my hypothesis is that you can't fake everything or have, you can't basically attack everything at once. Therefore, all the sensor data and the analytics that go with that. So if I fuse, in my case, say electro-optical and infrared data, you could create fake video data, but now you've got to create the exact perfect way of having a deep fake for IR imagery. So if we have good analytical tools that do the representation from different forms, you'll prevent bad data from overtaking the results. Now you mentioned voting from Kevin. That's actually a fundamental thing we did in comm theory, which is turbo codes, right? So if you send the message multiple times and then have the parity bit, it'll determine if you got the bad data on the network. And so we need to have methods of that kind of ability to come through. And then lastly, the third case is we know from engineering contests and other things that certain things becoming exciting when they win the contest or they do well. So deep learning took over in 2012. We need to have similar use cases and experiments for people to compete and compare, such that maybe my ideas aren't the best, but someone else's that performs well is exactly what is needed. So with that, we try to work on challenge problem data that the community can use and then replicate to have comparable performance analysis.
Mm-hmm. Thank you. Thank you.
Okay, that was a great answer. So next question is, what is the most important training for an undergraduate student and then a graduate student to work in the field?
So I'm going to give you this comment and then you guys can take it for what it's worth. But, you know, the idea is that physics, right? Too many people these days are just running data analytical tools. They don't understand, you know, the background of the physics. Now, that could be a biased opinion, given that I grew up before there was a lot of data analytics and there was, you know, a lot of signal processing that we did. They forced us to do all the math without the computing. And so you had a grounding in the physics. In this way, if there was problems with your software or data analytics, you can go back and think, okay, what does this really mean, right? So if you have a good understanding of the camera models and other, you know, Fourier transforms, that'll help you out in the end, because it looks like too many people are jumping straight to the software implementation and not understanding, you know, of the skill set. So if you look at the question here about the math, right, there's obviously going to be key people that understand optimization theory, regression analysis, and all those are going to be important as well. But bypassing that in your undergraduate studies will probably limit you in the future, because something's going to go wrong and you don't really have the time or the freedom to explore these topics on your own. So you might have to go back and get the math book and then, you know, start over to figure out what's wrong. And that all that time to go backwards to figure out how to fix your software might take more time than if you go through the training in a manner. Now, if you look at my skill sets, I just want to highlight this. People wonder why I have so many degrees. Well, you know, I wanted to explore different things. And I thought, you know, I'm going to get the best, most efficient way of learning by taking it from a professor who knows exactly what they're doing. And within, you know, the 8 weeks or 12 weeks, I'm going to run through their course and I'm going to learn exactly what they have. So within, you know, cost things, I took, you know, 350 college classes because I thought I'm going to learn quicker that way by someone guiding me through it. And now you have all these online opportunities to learn these things, say from Stanford and stuff, and get the certificates without much cost. So I would recommend someone, you know, augmenting their studies with some of these online, you know, short courses that force you to do some implementation and problem sets so that you internalize the concepts.
Yeah, that's good stuff. So do you want to, I think you covered this question a little bit already.
Well, I was looking at that one. So I was just trying to, you know, remind people and the students that,
yeah,
you know, I grew up as a mathematician and then, you know, so I think of things that way, not as a software person, but too many times, you know, we're getting results and the results are bad and all the people that are sitting around there are software people. So then when you have to go back and figure out how to correct it, it's usually that graduate student who really has a mastery of the math that says, okay, this is why I think it's going wrong.
So then what are the qualifications to work on projects for defense, security, intelligence applications?
Well, this one's a kind of a business issue, right? You know what you're best interested in and where you can come from. So in one case, might be an example, as I was telling someone yesterday, is they have a language benefit because they know 3 languages. So if you're going to do, you know, implementation machine learning over different languages, a lot of us focus only on English. But then when you're actually exploring other groups, and then as I highlighted throughout this, right, there's cultural influences, there are other things. So just, you know, play to your specialties to augment, you know, what it would be. And if, you know, you have friends or colleagues that work in, you know, security, say police officers or something, leverage their needs and to be able to do that. And in my case, you know, medicine is my example where, you know, I continually ask about, you know, how is the physician going to use these kind of things? Because then I can bring that to the design and development of the machine analytics. And then how to learn a new subject. Well, that's also, you know, I can't quote someone, but, you know, the best way I learn about something is I just write about it. So I force myself to give a presentation. So in this presentation, I started with scalability and I ended with certifiability. So by Dr. Zhu here forcing me to give this presentation, I actually explored like maybe 40 journal articles to come up with what I thought would be meaningful to this audience to learn something new, as well as complement with something that I've already published. And with that, you know, you just force yourself to learn by doing.
Thank you. I appreciate it.
Yeah. Okay. Do you want to elaborate more on the impact of utilization in the context of AI?
Well, again, the data that you choose determines, what's going to be, how the AI is going to be perceived and what's going to be the output. So if you work with your users up front, then you can structure the data of importance and then deliver something there that there's going to be useful. So in my case, I'm working with the Cape Cod Fire Department right now to deliver some tools and techniques. And we're working with them to figure out, what are they really interested in? And we're building up that human and machine teaming, just like we did for the intelligence community, by working with them to ask what they need, what they want, and starting with them right away versus designing something that we think is interesting and then, hoping that they're going to use it in the end.
Right. So what are the biggest challenges you guys have faced when it comes to human machine AI teaming?
Well, consistently the people that the engineers don't appreciate the users at the other end, right? So the counter example is being able to use your Google to determine where you should go. So when you do your navigation and you say, I want to go to this point, and Google does a JISC's algorithm and basically tells you how to get there efficiently, you at first say, okay, well, that's interesting, but I'm still going to use a map. Then over time, you realize that they've incorporated all the accidents, the one-way streets, and you get there quicker. So now you basically trust your Google derived route planning for you because it works well. And so with our humans, we need to figure out what they actually want and what they need. So the challenges are to work together to figure out, what machine analytics really helps them do their job and what machine analytics seems exciting to us as engineers, but really confuses them or makes their job more difficult. And the key element there is false alarms. You create too many false alarms and the human's going to be like, well, I can just do this myself. I don't need to have a machine output a bunch of spurious information that pushes me in the wrong direction.
Right. Could you give an example of an AI system? You mentioned earlier with the over-trusted and under-trusted systems. What's an example, if you can give, of an under-trusted system?
Where they don't.
They don't trust it as much as they should, I guess. Yeah.
Yeah, exactly. So in this case, there's a lot of machine analytics that go with imagery data that's collected well. And if you were to present the data to the user, say on a non-cloudy day, everything works well. Then they expect it to work on a cloudy day. So then the machine analytics, they try to run it when there's clouds or other obscurations in the way, and it doesn't work. So now they undertrust it because their performance that they got both on the good days and the bad days means that they don't want to trust it and they'd rather have the video for themselves. If we basically said, hey, we're going to manage expectations and said, this works really well, then there's no clouds. And if there are clouds, then don't run the machine analytics. And how do we get that information? Well, the weather information is widely available. So they can determine if there's a cloudy day or a non-cloudy day to determine if they should spend time looking at the machine output, say an uncloudy day, versus just trying to figure out when it's appropriate and the clouds move away. So that it's undertrusted mostly because you're presenting all the cases to them and then they expect it to do everything, whether it's cloudy or non-cloudy. Whereas if we told them up front with the contextual information that it works great, when the weather's good, but it won't work well when the weather's bad, then they start to trust it more and know when to appropriately use the machine analytics to help them do their job.
Oh, okay, that makes more sense now. So another question that I had was, what are the main issues and some of also the big solutions you guys have when it comes to domain changes and transfer learning?
Well, I mean, it's a contemporary research topic.
Right.
I encourage anyone to sign up as a summer employment or to work on that. And, working with experts such as everybody on the call here to come up with ways to be able to do that. So in the case of the transfer learning, obviously, if you try to expect it to go and transfer from one domain to the next, that's a leap too far. So we need to, that's why they now call domain adaptation to try to bridge that gap. If you take a student and you say, we're going to train you in Spanish And now, we hope that language knowledge you have works in Chinese, right? It's too difficult, a bridge too far. So we want approaches that, people manage this to build along those lines. And I'm interested with everybody on the call to, come up with strategies, but I don't think we have solutions yet.
Okay, I got you. It's one of those things that's like freshly developing.
And the same thing with explainable AI, right? I just put out 5 or 6 papers on that topic, and tried to work with groups to be able to determine that. And then, I want to end or combine this, is that what I think is explainable is not exactly what the user thinks. So even if I come up with a metric for explainable, we're going to need to test it. So with this MAST multi-source AI scorecard table, we want to improve that table, make it somewhat standardized. It could change for all I care, just as long as we are working on the same playing field. But if we're going to measure explainability, we also have to have a common metric that we all understand and all mathematically agree that will be the appropriate case. And so I tried to highlight that, yes, people can put out all these documents and mandates and say, we want it secure and trustable and all that kind of stuff. Sounds great, but we have to mathematically describe those so there's repeatability, measurability, and then ultimately be able to certify something meets these metrics for testing evaluation.
That really answers the question. Yep, thank you. And just want to say thank you for a very informative talk. It was a lot of insights into the different AI and the structures and all the different research that's going on.
Yeah, thank you, Erik. That's also what I want to say. So we are going to put this online on YouTube. So for whom who missed this, your friends who cannot come here today, to be able to watch it later. All right. So again, thank you, Erik, and thanks everyone for coming here for the talk. So I know it's a little bit over time, but hope everybody enjoy your lunch, late lunch, and enjoy the rest of the week. All right.
And if, like I say, if anybody wants to follow up with me, just send me an email. And when the travel things open up, I'll be happy to visit and have further discussions
Looking forward to meet
with
you.
your group.
Sounds great. Thank you, Erik.
All right. Okay. Take care.
Hmm?
You.